Okay, uh, so let's start the session today. I hope the screen is visible right now. So good evening and welcome to this 7th tutorial of the course Materials Characterization. I am Sabyasachi Panda from the Department of Metallurgical and Materials Engineering. And like we have done for the previous sessions, we'll first go through the concepts taught by the professor throughout the week, and then we'll solve some tutorial problems to understand those concepts, right? And yeah, so before going into the concept, yeah, so please keep the mic mute. Okay. So before going into the concept, I want to correct myself. I think I put one formula wrong in the last class. The formula for the lambda and wavelength, lambda and the voltage formula. So that formula I have put, I missed the square root of that formula, which is correctly I think correctly pointed out by Mr. Prahlad in the mail. So I think some of the answers, two of the questions in the assignment were given, the answers were given by not putting the square root formula there. So that formula actually tells us that the correct formula is 1.5 divided by the v plus v square into 10 to the power minus 6. So this is 1, and the correct formula is the whole total of 1 by 2. So the square root will come, and entire thing, I last time I missed the square root on the entire expression. Only I have given the square root of this expression, which was not correct. So thank you for pointing that out. And so you can use, so this is the formula that you can use. But if you want to assume something, if you want to approximate the value of lambda without calculating this big value, you can simply put 1 by 5 divided by v. But in that case also, you have to take the square root of the entire expression, right? Why from here, how you can convert it here? Let's say I am talking about an accelerating potential of 20 kilovolt. Then in that case, if I am putting this 20 kilovolt here, the formula will be 1.5 divided by 20 kilovolt will be 20,000 volt. Okay, so here the v is the accelerating potential, 20,000 volt, plus here v square, if I am talking about, then 20 into 10 to the power 3, this is square, into 10 to the power minus 6. Okay, and the formula will be entire 1 by 2. So here you can see 1.5 divided by 20,000 in the denominator. Here if you see 20 into 10 to the power 6 into this is 20 square into 10 to the power 6 into 10 to the power minus 6. So this expression would be there, and whole expression, the square root will be under over the whole expression. So here 1.5 divided by 20,000 plus so here it will be 400. However, 10 to the power 6, 10 to the power minus 6, they will cancel out each other. So this expression would be eventually 1 by 2. So here we are getting one value as 20,000, another value we are getting as 400. So that is why so 20,000 is far larger than 400. That is why we can directly, instead of putting this 400 in the expression, so directly you can use this expression similar. So this expression will be close to 20,000, and the expression would be 1 by 2. So last time I have put the wrong formula, so I'll talk to the team, and the grace marks will be given for that, because I think the answers are given wrongly. Okay, so yeah, so this is what I wanted to clarify. So now coming to the next session. Yeah. Okay, so this was the problem, this was the mistake from our side that I wanted to clarify. So next we'll go into today's topic, which is regarding X-rays, right? So we'll start the X-rays. Okay. Just give me 1 minute, I'm getting in call. Just take it and come back to it. Yeah, sorry for the discontinuity. We'll start the session. Okay, so today's session is about X-ray diffraction and what are the parameters, like how we can characterize our material using X-rays. So yeah, before going directly into what are the diffraction condition, what are the how the scattering happens, from scattering what are the chances of interference. So this is just a typical. This slide contains a typical historical perspective of X-rays. So as we know the X-rays, it has been discovered by the scientist. Okay, his name is Wilhelm Conrad Röntgen. Okay, so he was the first person who discovered the X-ray, and this discovery happened in as you can see in 1901. So he actually, the discovery happens sometime around 1900 1895, sometime around this, the Christmas of December of 1895. Then subsequently it took time for the scientific community to so it took some time for the scientific community to understand what are the rays that is coming from the material, and then finally in 1901 the official discovery of these X-rays have been accepted. And then you can see after the discovery there are lots of scientists took interest around Europe and around the world. And you can see in so from 1901, so from this time to 1936, let's say within 35 years of the discovery of X-ray, so 15 Nobel Prizes here, where the Nobel Prizes in physics, chemistry and medicine, whether it is based on the fundamental understanding of X-ray or how the application of X-rays are generated. So within 30 in a span of 30 years, you can see like 15 Nobel Prizes are given to different scientists. So that was the that was the craze of X-rays, you can say. And some of the notable development and some of the notable expressions or laws or equations are given by this scientists which I have mentioned it here. One of the most important scientists is Max von Laue. So he first so around Jen, what he did, he discovered the X-rays. And in 1914, Max von Laue, he was a scientist, he is also a he was a physicist actually. So he discovered that how the diffraction of X-ray can be influenced by crystal orientation. So basically he was the first person, or he was the first scientist to give us the knowledge that using this X-ray we can we can get different shape, we can get the different crystallography nature of our materials. Then so that is called Laue's equation. So he has given three equations. Then comes in 1915 William Henry Bragg and William Lawrence Bragg. They are father duo son. So both of them for the determination of crystal structure using X-ray, right? So they also contributed significantly. And the Bragg's, the famous Bragg's law that we are hearing, so this has been named after this father duo son, William Henry Bragg and William Lawrence Bragg. So and C.G. Barkla, M. Sigban, and Compton. So we must have heard about Compton in the terms of Compton's scattering. So he was also a great physicist. And finally we must have heard about Peter Debye. So he also significantly contributed for determining the molecular structure. In Debye, I think we must have heard his name in Debye temperature range when we talk about gases. That what is the Debye frequency? So Debye temperature, in those terms we have heard his name. So these are some of these scientists who have contributed significantly by using X-ray or understanding how the X-ray happens in how the X-ray diffracts or scatters in materials. Okay. And this is also somewhat a historical perspective of X-ray. Like another thing is why the name has been given as X-ray, because at the time of discovery of X-ray, so this X refers to an unknown. When the X-rays were discovered, it was an accidental discovery by Röntgen. He did not know like what is happening, what kind of rays are coming out of these materials. So he was not sure about that. But so that is why in English X means we don't know. So when it so at that time Röntgen was he was not an Englishman. So initially the name was Röntgenstrahlung in German. But when that German name gets converted to English, so the name is X. So X means unknown rays. So at the time of discovery, no one knew what this kind of what these rays are actually, and how this discovery happened, because he was fluorescing a barium platinocyanide screen. So why the barium platinocyanide screen? Because at the time of in the early 1900 or in the around 1900, so there was a famous experiment many scientists were trying to work on, that is called Crookes tube. So that Crookes tube is nothing but they are applying potential. So this group applying potential across two electrode, and they were just extracting electron. And so these are cathode, the electrons are called as cathode rays. And but the penetration power of these cathode rays, or the electrons which are coming out from one side, let's say from cathode to anode, that was very poor. And but when after a certain after a certain time, accidental discovery of Röntgen, when he was also doing some experiments using cathode rays, what happened is that he got instead of getting this cathode rays, he got also some, in addition to cathode rays, he also got some other kind of rays. So that is why he has named it as X-rays. That means it was an unknown rays. So so the different types of tubes he was using. So cathode, this is Crookes tube, another tube which was also known as Gisler tube. So these are the different types of tubes which people were working, or scientists were working at that time for to do some experiment with the electron. Okay, so by doing this kind of experiment, Röntgen discovered the X-ray. And so yeah. Okay, so we'll see now how the production of X-rays after the historical perspective. We'll see how the production of X-ray took place. So the X-ray production is nothing but what Röntgen did. He produced he put extremely high potential between anode and cathode. So one is, anode is connected to the here positive terminal of an electrical circuit, and cathode is connected to the negative terminal of the electrical circuit. So when that anode and cathode when they are connected like in the order of kilovolt, then in that case what happened, some electrons will be going from cathode to anode because the positive potential at anode will be very high, right? So when these things happen, when these electrons are going and electrons are having charge of E, that means 1.6 into 10 to the power minus 19 coulomb, and when they are given a potential of V, then they are having potential energy of EB, and when they are having potential energy of EB and this positive charge is attracting them, then they will start going in this directions, right? And this potential energy when they starts moving will be, they will be having some amount of kinetic, they will be slowly accelerating and they will be gaining some amount of kinetic energy as well. That means these electrons which are leaving the cathode, let's say here I am writing cathode as C and anode as A, these electrons which are leaving cathode at a extremely with the help of an extremely high positive potential, they are highly energetic beam, right? So when these highly energetic beams are going and hitting this anode material, at that point only this X-rays are coming out. How these X-rays are coming out I will show in the next slide, but this is the setup that he used and this is the setup we still currently use, because this is the basic principle of how these X-rays are getting generated. And an extremely high potential is given between anode and cathode, and due to that the electrons are extracted from cathode, and then and this cathode is called as filament, right? And so after that they will be going and hitting this anode material, out of which this X-ray will be generated. However, the generation of X-ray, when it happened, the efficiency of X-ray generation is less than 1%. That means rest of the 99% of the energy, so these electrons are highly energetic beams, so rest of the 99% of our energy, it is getting wasted in the form of heat. So that is why whenever this X-ray generation happen, so we had to cool this entire setup using some coolant. Generally we cool it using water. So this is the basic principle of X-ray generation. A positive potential is given, a highly positive potential is given, and due to which the X-rays from cathode side will be not X-ray, the electrons from the cathode side will be accelerated and they go and they hit this metal anode, right? So this when they hit this metal anode, X-rays will be generated. And remember, this metal anode which we are talking about, this thing is called sometimes as anode, sometimes this thing also is called target material. So you, right? And this anode and or the target material, whichever X-ray we are getting, always getting, let's say I'm talking about copper X-ray, let's say I'm talking about cobalt X-ray, let's say I'm talking about molybdenum X-ray, vanadium X-ray, any kind of X-ray that I am talking about, that means this I am referring to this anode material, because the X-ray which is coming out of my material, so that material is the anode material. So that is why if I am talking about, let's say, molybdenum X-ray, that means my anode is made up of, or my target, sometimes people call it as anode, sometimes people call it as target. Why target? Because electrons are going and hitting the anode material. So if this thing is taking place, if I am saying that my molybdenum X-ray I am using, that means my anode is made up of molybdenum and it's a pure metal anode, right? So it's a solid anode. This is the conventional X-ray, but nowadays also liquid metal anode are available to increase its efficiency. Yeah, this is the fundamental generation, the fundamental mechanism of generation of X-ray. And as we can see in the electromagnetic spectrum, so X-rays are here, X-ray are here. So the definition of X-ray is, X-rays are high energy electromagnetic radiation. X-rays fall under the electromagnetic spectrum. So X-rays are high energetic electromagnetic radiation whose energy vary between 100 electron volt to 1 mega electron volt. Okay, so this is the and 1 electron volt, when we are trying to convert it into joule, which is the SI unit, then you can see coulomb into volt. So 1 electron charge is 1.602 10 to the minus 19 coulomb into 1 volt is 1 volt, then 1.602 into 10 to the minus 19 joule. So this is the fundamental definition of X-rays, and here X-rays are the electromagnetic spectrum whose wavelength lies between 10 to the power minus 19 to 10 to the power minus 11 meter. Okay, so between these we have categorized them as soft X-ray as well as and hard X-ray. So generally in conventional laboratory around the world, what we use, it is a soft X-ray. In synchrotron sources, if you have heard about those synchrotron sources, they are using hard X-rays, right? So here you can see I put the synchrotron thing, but in conventional laboratory we are using these soft X-rays, which are sufficient for us to determine the phase or crystal structure of a material. And so this is a basic principle of generation of X-ray I told, and this is a little bit complicated schematics of this X-ray. Since electrons can be scattered by gas molecules, because the electrons gas molecules and different particles also in the air, so that is why a vacuum chamber is needed, and it has been sealed by glass. You can see here, this is water is coming and water is going out, because continuous water should be coming and then taking the heat away. Otherwise the heat generation in the metal anode will be very high, and due to which our efficiency will decrease, which we don't want. And here it has been the entire setup, the entire X-ray generation is that setup is kept in a vacuum. And here you can see there are different there are different components are present here. One component you can see here is window, that is called beryllium window. So this beryllium window is used because beryllium is transparent to X-ray. So whatever X-ray, so here you can see one is the positive, so the anode is here, okay, and the cathode is here. So when we apply extremely high potential between them, then the electrons will come in this direction, hit the anode, and then some X-rays will be generated, and X-ray will be generated in all directions. So that is why this window is given. This is a beryllium window, because beryllium is transparent to up to a certain thickness, beryllium is transparent to X-rays, right? And since we will be using generally people use a solid anode, then what will happen after, let's say I'm using a solid anode like this, and continuously high energetic electron beams are coming and hitting my anode, and X-rays are getting generated. Then what will happen, there is a scoop, like we eat ice cream. So after a certain period of time, this scoop formation will happen. When this scoop formation will happen in a solid anode, then what will happen, the efficiency will go down. We don't want that, because this is a very expensive setup, this X-ray generation. So we don't want that. So people have nowadays companies have adopted a rotating anode tube, so for greater power input. Because what will happen, let's say this is a rotating anode tube. So first time my X-rays, my electrons are hitting at this point of this anode material or the target material. Let's say it is rotating in this direction. So when my electrons will be hitting at this point, but if it is rotating, then after some time, let's say I am talking about my point A, after some time my point A will be at this position, right? So another point from, let's say, point B, this is point A, will be at this direction, and at time t is equal to 0, my A is this, B is this. Then at time t is equal to t dash, if I am talking about, my A will be here and my B will be occupying this position. Okay, so that is why I do not have to worry about this scoop thing, about the X-ray generation, and my X-ray efficiency, the production of my X-ray will also be high. But in that case, if you are using rotating anode tube, then the cost also is very that will also go higher. Okay, generally the potential that we use here 40 to 80 kilovolt, and the current that we use is 25 to 50 milliamps. So this is the typical this is a conventional X-ray diffraction laboratory parameters that we use to characterize our material. And what happens, I told here that the electrons will go and then hit the pure metal anode, and then suddenly the X-ray comes out. But what is the science behind it, what is the principle behind it? It is like, let's say this is my incident electron. So this electrons is coming from cathode, Okay, so it is highly energetic electron since it is coming from the cathode, and then this is let's say this is an inner cell. This is so this whatever I am talking about, this is my target material or anode material, right? So this is the inner cell, this is the outer cell. Okay, and my incident, highly energetic incident beam from this this is coming and hitting this inner cell electron. Now what will happen, since it has carried some energy, which one, this one is has carried some energy, it will if it has sufficient energy to knock out this electron which I am talking about, it has knocked out this electron from its position. Now that it has knocked out this, let's say inner cell is K cell, let's say this is K cell and this is L cell. Now that it has knocked out the K cell electron, there is a vacancy present here. Okay, in the K cell there is a vacancy in the dotted line. Now to fill up this vacancy, what will happen? To fill up this vacancy, the electron which was there earlier from the L cell, that means I am talking about this electron, what it will try to do, it will try to jump to from here to here to fill the vacancy. Why? Because you don't want any vacancy, since the highly positive nucleus is there here and it is pulling this outer cell electron with a high positive force or positive attraction will be there between this nucleus and the negatively charged electron. What it will happen, from L cell to K cell there will be a jump of the electron, and while this jump happens there will be some energy going out, and this energy is known as the X-rays, but this energy is known as actually characteristics X-ray, which has been written here. Okay, then so this is the fundamental of the X-ray generation. But we have to remember that any accelerating or decelerating charged particle emits radiation, right? So when we are talking about that this electron from cathode, from here it goes and hit this inner cell electron, they will also be spread giving some amount of energy, and they will also be producing some radiation. So that radiation is known as continuous radiation. Similarly, after knocking this inner cell electron, both this electron which is going from the cathode, it will reduce its energy. So its energy is also reduced, and this K cell electron which was earlier there, when it will be accelerating, this will also emit radiation. That radiation is also known as continuous radiation. Why? Because that amount of energy which this electron from cathode has transferred to this K cell electron, we don't know. Only what we know, that the energy is sufficient enough to knock out the K cell electron, but what is the amount of energy, we don't know. So that is why any accelerating or decelerating charged particle will emit radiation. Those emitted radiation is known as the continuous radiation. When there is a vacancy in the inner cell K cell, and then there is a jump from outer cell electron, that means L cell to K cell or M cell to K cell, that amount of energy is fixed energy, and that radiation is known as characteristics radiation, and this is what we call it as X-ray. Okay, so this characteristics radiation, we use it for our to characterize our materials. And this continuous radiation is sometimes also called as Bremsstrahlung radiation, or it is in German word, or sometimes it is called as braking radiation, or else also another name is white radiation. Right? Why white radiation? Because like white light is spread over a range of wavelength, similarly this continuous radiation is also spread over a range of wavelength. However, this characteristics radiation, because the energy between L cell and K cell for a particular material is fixed, the energy difference between L cell and K cell will also be fixed. So that is why this radiation is known as characteristics radiation, which we use. So whatever X-rays that we are going to use, so we only use this much radiation. Okay, and since this is a fixed energy, so we know that energy is equal to hc by lambda. So this is what called as monochromatic radiation. Okay, and if we want to draw the intensity versus the wavelength here, then the curve will look like this. Okay, here you can see E is equal to hc by lambda. That means as you decrease the wavelength, you can see the wavelength is an angstrom. Okay, as you decrease the wavelength along this direction, the energy will be keep on increasing. right? So here the intensity will also be increased. So the curve will look like somewhat like this, and initially the curve will be looking like this. Okay, then when you start increasing the potential difference between them, then at a certain point the curve will start looking like this. Okay, so this is a typical curve X-ray spectrum of any particular material. Here one interesting thing to note, that when I am applying a voltage of, let's say I am talking about a molybdenum material. Now molybdenum material I am talking about means I am taking my anode or my target material as the molybdenum. I don't care about the cathode and other circuit. Now I am talking about the molybdenum anode or molybdenum target. So when I am applying a potential of 5 kilovolt to the molybdenum, you can see I can that energy is not sufficient to knock out a KSL electron. So that is why I am getting a continuous spectrum here, right? That is a white radiation or a breaking radiation. Similarly, when I am applying 10 kilovolt, I am not able to get the characteristic spectrum. And all this kind of spectrum which I am getting till 20 kilovolt, if I am applying the potential between anode and cathode, that energy is still not sufficient to knock out a molybdenum KSL electron. But when I am applying 25 kilovolt, right, when I am applying 25 kilovolt of potential, then what I am seeing, I am getting continuous radiation, but simultaneously I am getting two sharp peaks named K alpha and K beta, and these sharp peaks are only known as characteristics radiation. Okay, and so yeah, here, so till 20 kilovolt I have I am not getting any radiation, right? And how will I see what is the intensity of the radiation that I am getting? The formula for intensity of radiation is I continuous spectrum is equal to AI Z V into M. So here A is a proportionality constant, I is the current, Z is the atomic number, okay, V is the accelerating voltage. Okay, so you can see at here various intensity, a mixture of wavelength of various intensity from the target I am getting, right? And as you can see, the peak of this each and every curve, this curve, this curve, this curve, and this curve, the peak of the curve, it was earlier here. For 5 kilovolt it was here, for 10 kilovolt it is here, for 15 kilovolt it is here, for 20 kilovolt it is here, for 25 kilovolt it is here. That means as I am increasing my voltage, right, that if I am increasing my voltage, then my intensity, it is slowly the maximum energy with which I am getting my radiation, it is also start going towards in this direction, it is decreasing, right? So that means it is increasing, that means my wavelength is decreasing, and if my wavelength is decreasing, my energy is also increasing. Okay, so this is a typical plot so like this, I am drawing it once again. This is a typical plot for an X-ray. So here it is X-ray intensity, and here it is wavelength. So these are the characteristics radiation, and all of these things are called as white radiation. Here one interesting thing is that at a certain point here, all of my energy which are carried from the cathode by the electrons, all of these things, so this is the, let's say this is the lowest wavelength of this corresponding to this 15 kilovolt of electrons, right? So this is the lowest wavelength, that means this is the maximum energy that my 15 kilovolt electron can transfer into my anode material. Okay, so beyond that I cannot transfer any more energy. Whether this energy is sufficient to knock out a molybdenum KSL electron or not, that is a different story. And what we have seen experimentally, it will not be able to knock out the molybdenum KSL electron. However, this is the maximum energy that I can give, or the molybdenum or an electron can give with an accelerating potential of 15 kilovolt, right? So that means this is the maximum voltage, this is the minimum wavelength it can give. So this minimum wavelength is known as short wavelength limit, right? So in short term it is written as lambda SWL. Short wavelength limit is the wavelength at which the electron coming from the cathode will be able to impart maximum energy to the KSL electron of a particular anode target or anode material. Whether that energy is sufficient to knock out that electron, we don't know, but this is how the short wavelength limit has been calculated. And how the short wavelength limit has been calculated, let's say I am talking about energy which is coming from the material, that means h nu. If I am talking about h nu, okay, h is the Planck's constant. Here h nu, if I am talking, that means hc by lambda. So this is the amount of energy that my electron has, my electron is carrying from the, when it is coming from the cathode. However, when it is coming from the cathode, we know that it has generated, when an electron is given an accelerating potential of V, then its energy is EV, right? And when I have to calculate this lambda, then what I will do, I am just writing it here. So let's say lambda, I am keeping it here, lambda will be hc by EV. So lambda SWL. Why I am matching these two? Because only when the total energy, the entire energy, when it will be expended to give, when this total energy, that is EV, when it is given to the anode material, okay, that is the maximum energy, and at that point only we will be getting the lambda SWL, that means the short wavelength limit. So when you will calculate, h is the Planck's constant, 6.6 into 10 to the power I think 10 to the power 34 or minus 34 joule per second, I'll tell you. And c is the velocity of the light, 3.3 into 10 to the power 8 meter per second is the electron charge. So when you calculate the lambda SWL, you will be getting some constant, let's say I am talking about constant A, and divided by V. Okay, so this is the short wavelength limit formula. Okay, so many times people ask that what is the short wavelength limit, only by giving the accelerating voltage. So you have to calculate the hc divided by E, this is a constant, and just put V. So that is the short wavelength limit. So now coming to the so this was the continuous spectrum, what we are observing it here. Now coming to the characteristic spectrum, what will happen to the characteristic spectrum is that if I further increase, let's say I have in molybdenum case I have got my so at 25 kilovolt I have got my characteristic spectrum. So that means I understood that there should be or there is a critical excitation voltage. When I apply that voltage only, my K cell electron will be knocked out, and this critical excitation voltage is target specific. You cannot apply one critical voltage, let's say 25 kilovolt of voltage, to knock out different material. It is target specific, and the amount of energy that that is coming out of X-ray, that means the difference of energy between L cell electron and K cell electron, that is fixed, right? So if the amount of energy which is coming out fixed, then the wavelength which is since E is equal to hc by lambda, this energy is fixed, that means this wavelength will also be fixed. What happens if I increase beyond 25 kilovolt of the potential, if I increase, then in that case also, since the energy between L cell and the energy between K cell, this is a fixed term, my lambda will be also fixed. Even if I increase this thing, the maximum intensity only will go towards the left side. Why? Because if I increase the energy, this continuous spectrum will be increased, but not the position of K alpha and K beta. Why? Because the energy between them is always fixed here. So if I increase beyond 25 kilovolt, what will, how the curve will look like? The currently these are like this. So in that case, the curve might look like, let's say, like this. If I go to 35 kilovolt for a molybdenum target, I am talking about, this is K alpha and this is K beta. Okay, so
can you please repeat it again? This is
yes,
sorry.
okay, since these characteristics, the energy I am talking about, so energy, the characteristics X-rays that I am talking about, the characteristics X-ray has a fixed amount of energy. So since they have a fixed amount of energy, the hc by lambda energy corresponds to hc by lambda. That means the lambda also is fixed for a material. So when you are plotting an intensity versus wavelength diagram, the K alpha and K beta, when let us say here from 25 kilovolt, I am able to see that beyond 25 kilovolt is the critical excitation voltage, and at 25 kilovolt I am getting my characteristics radiation. Okay, these are all continuous radiation which I am not bothered about currently. So I am getting characteristics radiation. But what will happen if I keep on increasing the excitation voltage? That means my voltage is still sufficient enough to knock out a k-cell electron in a molybdenum case. But in that case, what will happen? If I increase the voltage, my excitation voltage, my intensity of this thing, of the of my continuous spectrum, or the white radiation, they will increase, they will shift towards left. But since the energy between L cell and energy between the K cell, that is always fixed, so my lambda will not change. That means my K alpha position, the wavelength corresponding to my K alpha and the wavelength corresponding to my K beta, they will not change. Their intensity might change. That means intensity is nothing but photon count per second. Their intensity might change. Since I am talking about intensity in this direction, their intensity might change. They might go higher, but their wavelength will not change. However, the peak of the continuous spectrum, that might change. Okay, so for that region, always remember, when I am applying the voltage which is more than the excitation voltage, the increase in voltage does not correspond to the characteristics wavelength. Why? Because the wavelength corresponds to energy of the energy, and the energy between K cell or L cell, or let's say outer cell or inner cell for a particular material, that is always constant. So that will not change. So that is why increase in the voltage has nothing to do with the characteristics wavelength of the target. Okay, but there is like I said, one critical excitation voltage is specific to a target material. For molybdenum, 20 kilovolt is sufficient. But what will happen if I take 25 kilovolt in case of tungsten? Then in that case, we'll only get white radiation. Why white radiation? Because the radiation will always coming, whether it's an accelerating charged particle or a decelerating charged particle, the radiation will get. But the radiation is not sufficient. The energy which is being carried by the incident electron beam is not sufficient to knock out a K-cell electron for a tungsten. So just to give you a perspective that how much energy we need in terms of when we are talking about different materials, for tungsten you can see only we will get white radiation. For the excitation voltage, when I am talking about for copper, it is 8.86 kilo electron volt. Okay, when I am talking about the molybdenum, it is 20 kilo electron volt. When I am talking about tungsten, you can see how much electron we have to, how much energy, how much potential we have to give. So this is also another reason that we all might have heard that X-rays generally in the laboratory we use this copper X-ray. Copper X-ray is nothing but the anode material is made up of copper, or the target material is made up of copper. So this is one of the reason that we don't have to apply very high potential, because the moment we are going for high potential, similarly high we have to apply high power. We have to our power supply has also it also has to withstand that limit. So that is why we are using generally copper. Sometimes when in nowadays many places this molybdenum is also being used, because molybdenum has better penetration power as compared to copper. But this is also another reason that considering the energy perspective, we are using copper tube. Okay, and if let's say I'm giving 25 kilo electron, I'm giving 40 kilo electron volt, then still I'll not be though tungsten is a tungsten has a very high melting point as compared to molybdenum or copper, but still we are not using that thing, because we will only get in that case white spectrum, which is not at all useful to us, because we will not be able to extract the characteristics radiation. And remember, whatever radiation, whatever X-rays that we are saying that the X-rays are coming and hitting our material, those X-rays are nothing but K alpha X-ray. Okay, K alpha X-ray, K beta X-ray somehow we are able to manage. We are geometrical by applying some instrumental constant, we are able to get this K beta radiation out. So the K, when I am talking about that X-rays which are falling onto my sample, that X-ray is K alpha X-ray. And remember, what is K alpha and K beta X-ray? If the X-ray which is coming from L cell to which is generated when an electron makes a jump from L cell to K cell, that is called as K alpha X-ray. Similarly, there is chance also for an electron to jump from M cell to K cell. So in that case, what is this thing called as K beta X-ray. So now if you see the K alpha X-ray and the K beta X-ray, here from this curve, if I am saying, if you are looking at this curve, K alpha X-ray and K beta X-ray, both can happen. Other X-rays are also, other kind of jumps are also happening, but those are for those are very less in the quantity, so we are not currently considering that. So here you can see the K alpha X-ray and K beta X-ray, that is the X-rays which are produced when the electron makes a jump from L cell to K cell and M cell to K cell respectively. So what will happen, you can see L cell to K cell and M cell to K cell, the difference in energy between L to K and M to K, which of this is less, which of this is more. Here you can see the M to K, the energy, let's say I am talking about the electron, the energy from M to K is greater than the energy from L to K, right? Because L to K here okay, I have not mentioned that thing, but yeah, the energy, since M to K energy will be larger than the energy when an outer cell electron makes a jump from L to K. But here in this plot, if you see, the K alpha is having higher intensity and the K beta is having lower intensity. You can see here the energy is higher, that means the wavelength of M to K, which is, that means this is corresponding to beta and this is corresponding to alpha. The wavelength corresponding to this beta jump is left side of this wavelength spectrum. Okay, so beta is, in case of wavelength, beta is staying left towards to the alpha jump. That means the energy of this K beta is higher than the energy of this K alpha. But here we are seeing that the K alpha is having more intensity and K beta is having less intensity. That means the energy does not have to the energy, why this we are getting, then if the energy of the K beta is greater than energy of the K alpha radiation, then why we are getting more intense peak from K alpha? This is because the probability of jump of an electron when an inner cell vacancy is created at K cell, the probability of jump from L cell is much higher than the probability of jump from an M cell. So this is the reason we will get more of K alpha radiation. That means more of K alpha radiation we will get, our detector will be able to get, then we will be getting this K beta radiation. So this is why, though the energy of this K beta radiation is high, the K alpha radiation intensity is much more higher. So that is why always the K alpha intensity will be higher. Even now, so we have got K beta and K alpha. So somehow since the intensity of this K alpha is higher, we will be only considering K alpha. But even in K alpha, even in L cell, when I am talking about, there are two different L2 and L3, the subcells are also there. So the L3 to K jump, one electron can stay in L3 subcell, another electron can stay in L2 subcell. So the outermost subcell to K jump, that is what known as K alpha 1. Okay, the innermost electron, the subcell to K jump, that is known as K alpha 2. Okay, so geometrically we are able to remove this K beta radiation because we only want K alpha radiation. So though geometrically we are able to eliminate K beta radiation, unfortunately we are not able to eliminate K alpha 2 radiation from K alpha 1 radiation. Okay, so even you can see the thickness of the variation in the wavelength is less than 0.001 angstrom. That we even this much we want to separate them, and one will be K alpha 1, another one will be K alpha 2. So whatever information that we are getting, that information always carries from both the radiation, that means K alpha 1 and K alpha 2. So that is why when we do an analysis or an indexing of an X-ray diffractogram, we always strip K alpha 2 from using some commercially available software, right? So there is always an option of stripping K alpha 2. That means after that, which we will only getting the spectrum corresponding to K alpha 1. Okay, so this is what all about the characteristic spectrum of a that we will be getting from our anode material. Okay, and then comes the absorption of X-ray. So what do you mean by absorption? So the absorption is, let's say, intensity of my X-ray, it is I naught. If I am talking that my X-rays are coming, and so there are different kind of phenomena can happen when my incident X-ray is interacting with my material or my anode material or my target material. Different kinds of phenomena can also happen. So there absorption is one of the major phenomena. Mostly two phenomena are happening. One will be absorption, another one will be scattering. So these are the two phenomena, they will be mostly taking place. So since first we will talk about the absorption, how the X-rays are getting absorbed and what it has to do with studying the absorption of X-ray. Let's say X-rays are going, so the intensity of the X-rays, which is this is I naught I am talking about, and then intensity of the X-rays after getting some amount of I is the intensity of the transmitted X-ray. That's all we have to know. And this is the material which is placed on the path of this travel of this incident beam, and the thickness of this material is X. Then in that case, experimentally what we have observed is that intensity of this X-ray after traversing through a distance of X, when we are talking about how this intensity I will be able to get. If I somehow I will be able to get this transmitted intensity, then I will be able to correlate this thing with how much absorption my material is doing when it is interacting with X-ray, and that formula is given by I is equal to I naught e to the power mu x. So here I is the intensity sorry. So here I is the intensity of my transmitted beam. I naught is the intensity of my incident beam, which is known to me. E is the exponential, and x I know here. X, what is x? X is the distance through which or the thickness of my material, right? Here there is an unknown quantity which is known as mu. This mu is known as linear absorption coefficient. What does it signify? It signifies how much the material is able to absorb this X-ray into it. Okay, so and how this thing has been derived? This thing is derived di by I is directly proportional to x. Okay, directly proportional to I think no, dx. Okay, so this is the so minus dx here, directly proportional to minus dx. So this thing has been derived from here. The intensity, the decrease in the intensity will be directly proportional to the thickness. Since I am talking about the decrease in intensity, so a negative term is put here. The decrease in the intensity will be directly proportional to the distance traversed across the specimen. But now what I am seeing, that this linear absorption coefficient, I have no idea about it. So by experimentally we got to know that this linear absorption coefficient is dependent on three factors. One is wavelength, another one is physical state of the matter. That means whether the material is gas, whether the material is in liquid state, whether the material is in solid state, and another thing which is density of the substance. Since this is dependent on all these things, so what we did, instead of taking this linear absorption coefficient to know whether how much absorption our material is doing, there is another term we have introduced, that is called, since this is dependent on density of the material, right? So this is it is directly proportional to the density. That means if I am talking, if I can put this density down, and then it will be some constant, right? So that is why we have introduced another term called mu by rho, which is called as mass absorption coefficient. This is a constant term. And when we did this mass absorption coefficient, what happened? We got rid of this density of the material, and also we got rid of the physical state, right? So when we came from linear absorption coefficient to mass absorption coefficient, we only this mass absorption coefficient is dependent on the wavelength. And then what we did, this formula which I am talking about now, this has been converted to I is equal to I naught. Same thing, only instead of mu x we put mu by rho. Since we have put mu by rho here, then we have to multiply. Since we have divided rho here, then we have to multiply rho here into x. So what we have done now, I, that means the intensity of my transmitted beam will be equal to intensity of my incident beam here, and then mass absorption exponential to the power minus mass absorption coefficient, which is a constant for each and every material. Now you will say, how will I get to know? When we do some experiment, this mass absorption coefficient for different material is given. If you see the appendix of BD quality, the X-ray diffraction book, then you can see the mass absorption coefficient for different material, right? So this has been experimentally calculated. Rho is the rho means the density of that material, and x is the what is the thickness that your X-ray is traversing. So whatever we have told until now, this belongs to one material. But what will happen if we have instead of one material, what will happen if, let's say, I have two different set of material, rho 1 and rho 2, both are having some x, or let's say in this case rho 1 or rho 2. So in this case, what will happen? You have to mass absorption, we have to take the weight fraction of each and every element, right? If instead of one material, the different materials are there, then we have to take the weight fraction of the element, and then we have to calculate the mass absorption coefficient. Then only we will be able to know how much, after calculating that how much intensity our transmitted beam is traveling with, then only we will be able to know how much absorption has happened in this material. Okay, so this mass absorption coefficient of a complex material, or a material which has different elements in it, so weight fraction of the element you have to take into mass absorption coefficient of that particular element. Weight fraction of another element, mass absorption coefficient of that element. So similarly, we have to calculate that, and final mass absorption coefficient of the that compound we have to take, and then here this one we can put it in this equation, and we can calculate the intensity of the transmitted beam, right? And then why this absorption, and why it is important for us? Because we'll see this absorption coefficient, why it is important. You can see the absorption coefficient here, I am writing it here. Absorption coefficient is directly proportional to lambda q into zq, right? That means my mass absorption coefficient will increase as I my mass absorption coefficient is decreasing as I decrease this lambda, right? Decrease this lambda means I'm increasing the energy. Okay, lambda decreasing means I'm increasing the energy. If you look at this graph here, this is the energy first. So this has been split into two, top one, and let's say this is the bottom one, 2 is the bottom one. So as I decrease my mass absorption coefficient here, my this thing will, my lambda will also increase, and once my lambda is decreasing, my energy will also increase. If you look at here, if this is the wavelength, wavelength here. So this side, if I'm talking about, wavelength is decreasing. If I'm going this side, you can see 2.5 angstrom, 0 angstrom. So when I am coming from 2.5 angstrom, my energy curve, you can see it is increasing, right? Because lambda decreases means my energy will be increasing. Since lambda decreases means mu by rho also decreases. That means my mass absorption coefficient is also decreasing in this curve. But at a critical voltage, this is my critical voltage. Critical energy, my critical energy means what? My energy, whatever I am supplying to the cathode electrons, they are sufficient enough to knock out a KSL electron from, let's say, from a nickel. The material that I have taken now is the nickel. Okay, so when this thing happens, you can see with the decrease in the lambda, my energy is increasing and my mass absorption coefficient is also decreasing, because I am decreasing my lambda. But what happens after a certain period of time? When you are continuously decreasing the lambda or continuously increasing the energy, you have knocked out a KSL electron. That's correct. But while knocking out a KSL electron, also there are other phenomena which are taking place. One of the phenomena is photoelectric absorption, or that means it is a fluorescence absorption phenomena also that is also taking place. How? Because the radiations are coming. It is not necessary that the energy that you are getting, that means from L cell to K cell electron, that energy, that radiation for the jump of L cell electron to K cell electron, that radiation is coming out of the material. There is a chance that radiation, which is, let's say, this is an L cell, this is a K cell radiation. So the jump has happened, and you cannot always say that this X-ray radiation or for now I am not mentioning this as X-ray radiation, I am mentioning it as radiation, the characteristics radiation. This radiation, so this is the characteristics radiation. This radiation will always come out of your material and give you X-ray. This radiation will also knock out another electron in another cell, right? So this radiation will knock out another electron in another cell. Again, same phenomena happened. There a vacancy happened, and when that vacancy happened, another outer cell electron, let's say, staying it here, and that will also do a jump. So similarly, all these characteristics radiation, which are the difference between which are the characteristic, when these characteristics radiation are coming out as a result of jump of outer cell electron to the inner cell electron, these radiations are not coming out, they are continuously knocking another electron which are staying inside the material. Then what will happen, you will not get, though your energy after beyond this point, though your energy is increasing, but at this point what will happen, suddenly you are not getting X-rays anymore. You are not getting the X-rays that you are supposed to get in that because of this photoelectric absorption. What is the photoelectric absorption? Means the characteristics radiation are not coming out, rather they are knocking out other electrons in other cells in the same material. That means the incident X-rays are coming, okay, incident beams are coming. Instead of getting X-rays, they are inside the material, they are knocking each other out. In that case, what will happen, the absorption is increasing, and suddenly from here, which was the mass absorption coefficient, which was continuously decreasing here, suddenly what will happen, the mass absorption coefficient will make a jump. Why? Because of this photoelectric absorption. Suddenly this jump, it will happen, and beyond which, when you again increase, then again it will follow the same path. That means it will, energy is increasing, that means lambda is decreasing, and the mass absorption coefficient is also decreasing. So this kind of phenomena will occur at the critical energy. Okay, that means the energy which is required to knock out an inner cell or K cell electron, and this jump which is suddenly happens when the energy that you provide is sufficient to knock out a K cell electron. This edge is called as absorption edge. Okay, and this absorption edge is extremely important to us, because using the concept of absorption edge, we are always putting we are always using a term called filter in X-ray radiation. Okay, how we are using filter in X-ray radiation? Let's say I have got so I have, okay, there is not enough space, just try to look into this. Let's say I am getting K alpha here and K beta here, right? Okay, this is a continuous spectrum. Okay, so this is the K alpha and this is the K beta, this is lambda and this is intensity. Let's say my absorption X-ray which is coming out, so this is my the radiation of my X-ray. Now if I put some material which will be having the absorption S in between K alpha and K beta of a material, that means I am effectively allowing this K alpha radiation to go out of this material after interaction. So I'm just give me I'll just change the color, let's say this color. So this is my X-ray. Okay, this is this absorption S which I am talking about, right? This absorption S which I am talking about, this is my material which is on my path of the X-ray, right? So when I am keeping this kind of thing, then the only thing I am getting is K alpha here, because what it does, this material, what it did, it shielded out all the unwanted radiation, all the white radiation. So only radiation that I will get is this one, and this, based on this absorption edge concept only, we have developed all the filter that we are talking about, we have developed. And generally, why I have taken the nickel filter, because for copper K alpha radiation, nickel material is used to filter out the K beta radiation from the K alpha and K beta radiation. Okay, and for first row transition element, there is a trend, it has been seen for first row transition elements, if your material from which X-ray is coming out is Z, then the filter material, the filter through which your X-ray has to go, so that only K alpha radiation you will get. Why K alpha? Because we want our X-ray to be as monochromatic as possible. So if this is your X-ray material, then the filter material that you will get, you have to choose is Z-1. That means X-ray, the Z means atomic element. So copper is 29. So copper is, then nickel is 28. This is the copper is the X-ray material, nickel is the filter material. So filter, similarly for second row transition element, it has been seen that instead of Z-1, it has been observed that Z-2 is the filter material. And how the filter material are chosen? Based on the concept of absorption edge. Okay, and this absorption edge is based on mass absorption coefficient. So these absorption edges are natural X-ray filters, and it helps us to get monochromatic rays as possible. Okay, so now if I'm talking about an X-ray interaction with matter, let's say X-rays are coming, there are different phenomena which are taking place. One is absorption happening here inside the X-ray. Another thing is happening inelastic scattering, which I think you will study in the next week. And there is another thing which is happening is the elastic scattering also taking place. We'll study, and also transmitted beam. Transmitted beam is the direct beam. Okay, so elastic scattering is given by I think we will study, but I am just mentioning it here. It is given by Thomson scattering, and this inelastic scattering is given by Compton's phase shift. Compton's shift, not phase shift, sorry, Compton's shift. Okay, and the absorption equation is given by I is equal to, and you will get to know about these two equations in the next week. Compton shifts and Thomson scattering, that how the elastic and inelastic scattering are happening. This is my sample. If I am talking about, this is my X-rays. Okay, and this absorption is given by I is equal to I naught e to the power minus mu by rho into rho x. These are the formula. Okay, so effectively absorption plus scattering, these are the two phenomena which we have to consider when we are talking about X-rays. And then comes I want to see what two important terms which we will see in the next slide. Those are phase difference and another one is path difference. Let's say my wave is like this and it is traveling in the direction of x. Here I have mentioned it here, in the direction of x, the wavelength is lambda. At any point, let's say in the direction of x, at any point, if I have to calculate the the path difference, or at any point, since these X-rays are for electromagnetic radiation, it has both particle nature as well as wave nature. Why I am considering wave nature here? Because by considering the wave nature, I will be able to see the position or the difference in different phases at different time as well as at different positions, because a phase is eventually not phase, a wave is eventually characterized by its position and its time, right? So that is why I have considered this X-rays. I am considering now this X-ray as a wave. So when I am talking about wave, there is a wavelength associated with it, which is lambda, and at any point if I have to calculate the phase difference. Why phase difference I have told earlier, I'll repeat it now. If my path difference is there, then my path difference will give to phase difference, and phase difference is there, then interference will be there, and if interference is there, then I will be get net amplitude, whether based on the positive interference or the negative interference, and from the net amplitude I will be getting intensity. So eventually, if I know this path difference of my wave, which is traveling across the material, across different medium, if I know this path difference here, then eventually I will be correlating with it intensity. So that is why it is important for me to know about the path difference, and the path difference, how it is associated with the phase difference, 2 pi by lambda, and here lambda is the wavelength of my wave. Okay, so 2 pi by lambda, and since I am talking, let's say my phase difference at any point of time, my path difference is x. If I am talking in terms of this x direction, and at any point x, at any point, let's say my path difference is x, then my phase difference is 2 pi by lambda into x, right? So this is the difference, and remember this expression I have written considering that my wave is traveling in x direction, but in real lattice, it is not the case. My wave can travel in any of the direction, right? It can travel in 45 degree, 43 degree, 30 degree, 20 degree, 90 degree, 360 degree, any direction it can travel. What I will do in that case, to get to know the phase difference, right, I have to represent the in that here I have represented in terms of scalar. But when I am talking about any random direction, right, like this wave is traveling, okay, like this wave is traveling at any random direction, at any point I have to calculate, right? So if at any point I have to calculate, then I have to consider two things. One is the unit vector through which the unit vector, that means my unit vector my wave is traveling through. So if my wave is traveling through this, then I have to calculate the unit vector in this direction and the position vector at which I want to calculate the path difference. So there are two things important. One is unit vector and another one is position vector. So position vector means if I am talking about from origin, and if I am talking about a point R, what will be the position, what will be the phase difference in at a point R, then first I have to calculate the position vector and then I have to calculate the unit vector. When I multiply those things, so that will be giving me the path difference. That means my position vector as well as the unit vector, they will give me path difference, and same thing 2 pi by lambda, lambda which is corresponding to wavelength, that they will be giving me the phase difference in total, right? So this is how I, at random, any random direction, if I know at any random point, if I know the position vector of that point, and if I know the unit vector of the in the direction of wave, I'll be able to calculate the phase difference, right? And then
Sorry, just can you please again repeat that path difference interpretation, phase difference understand, path difference,
which
what basically, path difference, what is that basically? Can you please repeat it?
which one, the left side or
Path
right side?
difference, path difference, path difference. How to understand from this curve, this is a path difference.
This one or one, this one or this side?
Anything you can explain, that is both you can see that how the path difference to understand.
Okay, path difference. Okay, so
Yeah.
path difference, actually we will get the path difference by calculating geometrically. This is the vectorial notation I have given you, but the path difference eventually we will calculate it by seeing the how much path one wave has traversed through the distance. So
So
for now,
physically, I can understand this is my path, but from this curve, see, this is going by sinusoidal curve, correct?
yes, yes,
If you
it
ideally take it.
it can be sinusoidal. It can be yeah. Currently it's sinusoidal curve. Okay.
Correct. Now we know the phase.
Hmm.
So just because that usually if you take where it is touching, we can understand the phase difference. But from this curve, how to understand path difference other than calculation? Physically, anything is there? If this is the thing is,
Yeah, inside from this curve means from, let's say,
The
yeah,
distance
this.
between alternative crest and the trough, that is called as the path difference. That is the general definition of the path difference. Yes, sir.
Sorry.
The distance between the alternate crest and the trough, that we can call it as the path difference. Yes, sir.
No, no, no. So that need not be the path difference, because let's say okay, in this case if you are talking about path difference, then instead of this one okay, this so if I am talking about this curve, so currently this is a sinusoidal curve. So means that is why we can say in that sense that let's say at this point what will be the path difference between between a crest and trough. But if a sinusoidal curve is not, the perfectly sinusoidal curve is not there, then we cannot say that thing. But in this case, in this curve, you can say that the difference between let's say at this point, what is the difference between path between these two? We can talk in terms of that. Did it clear?
it's okay. Thank you.
Okay, we'll see how to calculate the path difference when I'm going to the diffraction. Yeah, currently, so this is the phase difference that I'm trying to note it vectorially. That how vectorially we'll be able. So we know the how to calculate the path difference. We'll see it in the next slide, in the subsequent slides. But how to correlate the path difference with the phase difference? So we have to take the position vector of that vectorially. We have to take the position vector of that, and then we have to take the unit vector, right? And then while calculating, and generally if I am talking about wave, then wave is if the wave vector once when I am talking about wave, then we have to take a generally in to avoid mathematical complications, we generally take one wave vector in real space, and then we talk about in its complex conjugate. Why we, let's say this G is my wave vector which is traveling in some random direction, and the path difference which is given by k into r. Here remember in the earlier case, here I have written k is the small k, but that means it is the unit vector. But then if I am associating this k with some wave vector which is having the unit vector in small k and the magnitude as 1 by lambda, so in that case I can write, so here is it is the path difference, right, k into r. So if I am writing my wave vector in G, then I can write its complex conjugate. Remember, these are all for mathematical simplicity. Okay, so and if I can write its complex conjugate as G star, and the G star will be e to the power minus 2 pi I kr. If I am talking about G is equal to a into 2 pi I kr. Okay, and complex conjugate will be this. Then what will be the simplicity for us when I am trying to calculate intensity, right? So this is a wave vector, this is another wave vector. When I am trying to calculate the intensity, then only I have to know the amplitude. I will not be bothered about the what will be the path difference or the phase difference, because I will be getting my intensity expression will be carrying out by only knowing the amplitude of a particular wave. Okay, and here the k vector which I am talking about, any random vector, it has the unit vector small k and the magnitude will be 1 by lambda. And remember, this magnitude of 1 by lambda, it will be helpful for us to understand the scattering phenomena in coherent scattering phenomena. Then then if we are seeing the scattering by an atom, let's say these are not circular, but okay, let's say this is the positive nucleus is there, and here this is an electron. I'm just putting it here, and here there is another electron like this one. Okay, and two of my incident waves are coming like this. This is the coherent scattering I'm talking about. I think we'll study about it in the next class. And the vector that I am taking it here, it is, let's say, S0 vector, the incident beam vector. And these are the electrons, let's say electrons, these are the electrons, and my incident beam vector is coming. So there are two chances. One will be, if I will put a screen here, if I put a screen here, if my beams are getting transmitted in this direction even after the interaction with the negatively charged these electrons, then there will be no path difference associated with this thing, right? If I, let's say this is a XX bar screen, if I put it here, there will be no path difference between, if this is one curve, this is two curve, there will be no path difference between here and here. But let's say now this, after interaction with this electron, they are scattered. And now if I want to put a screen here across this phase y bar, then I want to see what is the phase difference, or because eventually I have to calculate the path difference, then what will be the phase difference that is or the path difference that is coming. Here we can do a thing. Let's say this is origin. We will take this one as the origin, the nucleus, positively nucleus. So if you are seeing, and this is the 1 dash beam after scattering, this is the 2 dash beam after scattering. So if you see it here, okay, this is the perpendicular, this is just another perpendicular. So if I am talking about A and B, this point is C and this point is D. So 1 and 2 beam till A point and C point, they have traveled same path, right? And 1 dash and 2 dash beam beyond D point and B point, they have also traveled same path, right? And the okay, this is what I am doing. So till this one they have traveled, after this one they have traveled same path, till this point also they have traveled same path. So whatever the phase, whatever the path difference is there, that path difference is associated with AC, AD and BC, right? So if I am able to calculate, if I am talking that this is S naught incident beam and my scattered beam is considered in the form of S here, right? So how I will be able to calculate the path difference here. So whatever path difference I have between these two beams, this is AD is the path difference and then BC is the path difference, right? So this will be the total amount of path difference between the two beams, right? So how will I be calculated this difference, and this is this thing, this is R, okay? Remember, how will I calculate this value, this path difference? You have to multiply the unit vector in the direction of incident beam, right? The unit vector in the direction of incident beam is S naught, and then the position vector. If I am talking the position vector from here, then position vector is this one. So I can calculate the path difference S naught for BC, S naught, let's say R, I can calculate. So BC value will be S naught R. Similarly, AD value, if I have to calculate, the unit vector of the AD value will be S, and the position vector, if I am talking from here, the position vector will also be at this point, if I am talking, the position vector will also be R. So AD value, if I am talking, then AD will be S into R, and these are all dot products, okay? So AD value will be R. However, one R vector I am taking in one direction, let's say in this direction, and another R vector I am taking in another direction. So if I have to calculate, then if I am taking this direction as my positive direction, this direction as my positive direction, then the path difference that I will be getting S dot R minus S naught dot R, right? And if I have to if I have to do this, S minus S naught dot product R, so this will be my total path difference when a scattering by an atom happens, okay? So S minus S naught, there is an interesting term coming. Now if we draw, let's say my S naught vector was in this direction, okay? And so initially it was like this. So S naught vector was in this direction, S vector was in this direction. So if I have to calculate the resultant, so S naught I have to draw, and then this will be I have to draw. So S vector is this, and my S naught vector is this, and my S vector is this. So if I have to get a resultant vector here, so this vector will be S minus S naught, right? And here what I have got, S minus S naught, okay, in this diagram. So S minus S naught, if I am able to calculate this S minus S naught, then this vector actually known as the scattering vector, okay? So and if I give an angle of 2 theta, why I am taking 2 theta? It is for my mathematical simplification. You can take theta as well. There is no hard and fast rule that you have to take 2 theta always, because when I am breaking the 2 theta into let's say half, then I will be getting expressions like sin theta, cos theta, all those things. So that is why I am taking 2 theta. You can take any theta or theta by 2 as per your convenience. So remember, scattering vector is that vector which turns an angle 2 theta to make that incident beam as a scattered beam, okay? So this is what incident beam, this is the scattered beam, and this S minus S naught which turns this incident beam into scattered beam, that the vector corresponding to that is known as scattering vector. Generally we mention that as Q. So S minus S naught will be given by Q, and if I want to calculate what will be the magnitude of this Q, since okay, here it is not if I am now I have given that the s and s naught is a unit vector. If I associate an magnitude which we have seen here, the magnitude which I have associated is 1 by lambda to that unit vector, then this the magnitude of s naught will be equal to the magnitude of s, this one s will be equal to the magnitude of s naught which will be equal to 1 by lambda. That means this magnitude and this magnitude, it will be same. So when I am talking about that thing, I am drawing another here. Okay, this is my 1 by lambda, this is also my 1 by lambda. And how to calculate this thing? I have to draw a perpendicular. If I am drawing perpendicular and these two sides are equal, then this value and this value, they I am writing A, B, C, D. Now if I draw a perpendicular to D from B, then AD is equal to CD, right? In triangle BDC, since this is a perpendicular triangle, let's say 2 theta. Why I have taken 2 theta here? Because this will be theta. So I am talking about in BDC sin theta is equal to here DC by BC. So DC will be BC sin theta. What is the magnitude of BC I have taken? 1 by lambda. So I can put 1 by lambda sin theta. So DC will be, so this value will be 1 by lambda sin theta. Similarly, this value will be also 1 by lambda sin theta. So total Q vector, that is AD plus DC. So Q vector magnitude will be 2 sin theta by lambda. Okay, remember this is one of the most important expression, Q is equal to 2 sin theta by lambda, because it will help us understanding the how the Bragg's law has been depicted from Laue's diffraction condition. Okay, so these are the few. This is Q is the scattering vector, and scattering vector is s minus s naught, the difference between the scattered vector as minus the incident beam vector, and the magnitude is given by 2 sin theta by lambda, where lambda is the wavelength of the beam. And then comes Laue's experiment. So these are the few terms I want you to just familiarize with. I think we will go through those terms when we will be studying the elastic scattering and inelastic scattering again. But yes, they will be used here in Laue's experiment. So what as I said earlier, the Laue's experiment, Max von Laue, he was the first scientist to show us that X-rays can be used to determine the orientation of the crystal, and he did some experiment with the zinc blende structure here, and he got to know that along 4-fold axis, along 3-fold axis, different, he rotated the crystal, and somehow he got to know that so the orientation of the crystal determines the spot patterns. Okay, and since zinc blende structure, he got many different spots according to his rotation. He got this different orientation. He changed the orientation and he got different spot patterns, which made him think that what is actually happening. So his experimental setup is like this: incident rays of varied wavelength. He actually he kept a single crystal. The single crystal was zinc blende structure, ZNS, zinc sulfide, which is having zinc blende structure, and then he actually used it in a transmitted mode, not in a reflected mode. He used it in a transmitted mode, and he got to know that this spot indicating the coherent interference of X-rays by crystal planes. These spot whichever he is getting, it is not that randomly they are generated. When he rotated the crystal in some direction, then the spots on his on the photographic plate or film or the screen, we can say, they also got rotated. So that got him thinking that when there is some sort of relationship between the periodicity of the crystal and the spot pattern that is getting generated here. So what he did, so just to show you, let's say there are different these are the scattering center which are present here. Scattering center means these are effective atoms are here, atoms are present here. So what he did, let's say X-rays are coming like this, okay, and this is what I'm talking about in X directions only. X-rays are coming and then getting in this direction, and then finally if I'm talking that X-rays are coming in an angle of alpha naught, and then they are going in an angle of alpha n, right? So, and the gap between this is A, if I am talking about A. So, and these are all scattering centers. Scattering center means they are nothing but atoms present on a particular plane. So, if I am talking about that, then same thing I can associate with it. S naught is the incident beam vector, S is the scattered beam vector, then an alpha naught angle is the incident angle, alpha n angle is the scattered angle, and this, remember, alpha naught might not be equal to alpha n in this case, okay. So what he observed, same thing, that means if I have to calculate the path difference between these two, okay, if I have to calculate the path difference, if I am talking AB and here CD by drawing perpendicular, so the extra path that these two has gone, AD plus BC, right? So this is the path difference that he has to calculate. This is 1 and 2, let's say after scattering, this is 1 dash and 2 dash. So when you calculate this path difference when he calculated this path difference considering the unit vector, then what will be happening, this path difference will be giving you the value of, when you calculate it geometrically, then it will be giving you value of A into cos alpha n minus cos alpha naught, okay, is equal to nx lambda. Why nx lambda? Because we know that in constructive interference, so here scattering happens, right? For you to get a diffraction on your screen, for the constructive interference to get a spot on your screen, like he got all these spot, so this spot corresponds to the constructive interference, right, from Young's experiment. So the constructive interference should be happening. And how the constructive interference can happen? Constructive interference can only happen when the path difference should be equal to integer multiple of lambda or integer multiple of your wavelength. And since I am talking in terms of only x direction, then I am talking nx. What does nx means? Nx means the order of the order of scattering that is taking place across the x direction, and A is the distance between two scattering center. Alpha n is the angle of scattering, alpha naught is the angle of incidence. So when you will be calculating geometrically these two, so you will be getting A into cos alpha n minus cos alpha naught is equal to nx lambda, but this is a one dimension, okay. Similarly, if you can calculate, but we are not but he has not done this in one direction. Similarly, when I am talking in another direction, let's say y direction I am talking, then I am taking that the distance between two atoms are b, then similarly you will be getting cos alpha naught instead of beta n minus cos beta naught is equal to ny into lambda. Similarly, if I am talking in terms of z direction, you will be getting c cos gamma n minus cos gamma naught is equal to nz lambda, right? So that means the equations that he gave, these three equations, this is known as Laue's first equation, which gives us the condition for constructive interference, that means to get a spot on the screen, which gives us the condition for first in x direction. Similarly, this is known as Laue's second equation, and this is known as Laue's third equation, and these equations are derived based on the calculation of the path difference that is eventually giving us the constructive interference. And for the constructive interference to happen, the path difference should be an integer multiple of wavelength. When all these three equations are taking place, it is not necessary that, like I showed it here, like in one direction, since this is a two-dimensional plane, I am showing this thing in one direction. But here, if you look at this diagram, so when the incident beam is coming in S naught and the scattered beam is going in S direction, it can give a conical structure. Why? Because we are living in a three-dimensional world, and our material is also three-dimensional. So instead of getting a single line like here, the scattering line like here, we'll be getting a conical structure. Okay, and when you put a so this conical these cones are called as coset cones, and when you put when you put a screen, let's say like here, you will be getting only the ring like structure. Okay, and these rings are called as dividing. Okay, and when all the first equation, second equation and third equation, right, when all this third equation simultaneously, when they the simultaneously when all these three equation the condition of scattering for all these three equations, that means in all the three directions the scattering which is taking place, it is the path difference is an integer multiple of wavelength, then only the condition of diffraction takes place. Okay, so but the problem is whatever we have seen in though he has explained in terms of what is how we will be able to actually, we are actually getting spots, because spots are eventually connected to interference, and how interference is connected to the path difference. He eventually showed this using equation, but there are certain limitation. What limitation? In three directions you have to know ABC, that means the distance between the scattering center. Also there are nx, ny and nz, that means the order of scattering also you have to know, and then you have to alpha n, alpha naught, beta n, beta naught, gamma n and gamma naught. All these 6 plus 6, that means 12 parameters you have to know to calculate whether the diffraction is taking place or not. Okay, so to avoid these 12 parameters, what we are going after this after Max von Laue gave his proposition, there comes another scientist, William Henry Bragg and William Lawrence Bragg. They gave what? They assumed that these atomic planes, so these are atomic planes, so they assumed these atomic planes as mirror polished surface. Okay, so when they assume these things, instead of, so actual scenario, what is happening? Scattering happening. But William Bragg, what he assumed, the planes are mirror polished surface. So when they consider that these are mirror polished surface, my incident beam is coming like this, and then it is going. What he assumed, that instead of scattering happening, what is happening? Reflection is taking place. Okay, so that is why the Bragg's law is always called as the simplified version of Laue's diffraction law. So what is happening? He told that, let's say the interplanar spacing is d. Okay, and when you calculate this thing, let's say A, B, C and D, when you calculate the extra path that is traveling by 1 and 2, let's say this is 1 bar and 2 bar, it is BC plus this is BD. This is the extra path that has been traveled. And if I am talking, this is D, right? This is D, and let's say this is my theta. This is theta, means this is 90 minus theta, this is also theta. So if this is D, this will be given by, this BC will be given by D sine theta. Similarly BD will be given by, this is geometrically I am calculating the path difference, BD will be given by D sine theta. And this path difference for interference phenomena, for us to get a diffraction spot in our screen, constructive interference should have happened, and constructive interference, if it is to happen, then the path difference should be equal to integral multiple of wavelength. So this is how we are getting n lambda is equal to 2d sine theta, considering atomic planes are mirror polished surface, and then instead of scattering, only reflection is taking place. So that is why Bragg's law is called as an oversimplified version of Laue's diffraction laws. Okay, so here we can see that from the
Sorry, just interrupting.
Yes,
Now we are talking diffraction, correct?
we are talking
Bragg's analysis of
yes,
diffraction.
yes,
And other part is the simplified version of Laue's law of reflection.
now Laue's law tells us about the scattering.
scattering, and reflection, you are telling that this is also reflection also.
No, it has been assumed that the reflection is taking place because this beam is
Yeah,
coming.
because just 1 minute. So
Yes.
can you please how this reflection, diffraction, and those things are there and scattering here? Can you little bit three things
Uh,
briefly can explain? I need not to get visually. I need to get clarified.
okay, that is actually yeah. We can discuss that. Let me. I have put some of those information in the subsequent slides. But yeah,
Just for understanding. See,
yeah,
this
yeah.
is this is the on time for me also. 1 2 points I can clarify.
Yeah, yeah. I have put some of those information. Just wait till the class. Otherwise, at the end of the class, I'll tell you how they are correlated with each other.
Okay, thank you.
Yeah. So here what we are seeing that the Bragg's law n lambda is equal to 2d sin theta. So effectively Bragg's law is giving us law that n lambda is equal to 2d sin theta. So whatever we don't have to worry about anything, but we have to worry about only spacing between the plane matters for us to get a diffraction condition. And Bragg's law is represented only in two dimension, right? The incident beam and diffracted beam, they all lie in the, for reflection to happen, we know the condition of reflection in we have studied it, they all lie in the same plane, right? And X-rays are not, but in real world we know that X-rays are not reflected but scattered by electron. That means if whatever condition Bragg has assumed, is it wrong, or just to get a diffraction condition he has assumed a lot of he has taken a lot of assumption. And because in real life crystal planes are not shining optical mirrors where we are considering that all incident ray, reflected ray, and the normal to the reflecting plane, they all lie on the same plane. But in real crystal that is not the case. So is the Bragg's law which we are talking about, because we know that Laue's diffraction condition is true, but Bragg's law, after considering so much of assumption, is it correct or is it wrong? That so we'll see how the, okay, first we'll see how the diffraction plane, we'll go deeper into that. So let's say I want to calculate whether a plane, whether the atoms that is lying in the plane, whether they are giving, they are satisfying the condition of diffraction or not. For that I first need to visualize a plane, right? So if I am talking about, if I am taking a unit crystal here, right, in A direction, B direction, or in C direction, and if I am talking about 110 here, and this is a crystal that I have taken, then I can assume that, okay, this is one plane and this will give me the diffraction condition. But if I have to visualize, or if I have to think that how shall I visualize, let's say 130 plane, how shall I visualize a 350 plane, 356 plane? So that will be difficult for me to visualize, to know whether that plane, because each and every time I cannot, here I have drawn, let's say this is in one direction planes I am taking, this is one plane, this direction, and this is another plane. So I can calculate the path difference between them by drawing easily some by use of geometry. I can draw the path difference. But in this case, how will I do? Let's say in another plane 353 I am talking about, how will I calculate the path difference? So what scientists did then, to calculate the path difference, to represent this plane, because eventually planes are three-dimensional. To represent this plane, what they did, okay, they represented this plane by a magnitude. Let's say the plane is this plane is 110 plane. If I am talking about the 110 plane, then they represented this plane by the interplanar spacing of by the interplanar spacing from the origin, okay, by a vector whose magnitude, by how did they represent, initially represented by a vector whose magnitude is the interplanar spacing between the plane and the origin, right? So this removed us that three-dimensional plane. We don't have to each and every time, let's say don't have to take all these things. And if I'm talking about 343 plane, then you don't have to draw a plane something like this, and you don't have to do. Why? Because now we are representing a plane, a three-dimensional plane, by drawing a vector, okay, by drawing a vector whose magnitude is equal to the interplanar distance from the origin, okay. But there comes another problem. When we represented all those things, so here from this is a 3 dimension, we came to 2 dimensions, okay. But when we represented all the three-dimensional planes to the two-dimensional plane, to the two-dimensional figure by their magnitude of the interplanar distance from the origin get dense here. Then if I go to the higher order plane, then I will not be able to see, let's say 410, and this plane, this magnitude I am not able to visualize. So how will I know that whether the plane has whether the plane has been satisfying the condition of diffraction or not? Then yeah, these vectors representing all the lattice planes extremely dense at the origin. Though this has solved my earlier problem, but still it is not helpful, right? Then Ewald, the scientist named Ewald, he came with a proposition. With what proposition? Now, instead of choosing the plane to represent in the real lattice, he told us that we have to take the planes which are being represented in real space now, in real lattice. He told us to go into reciprocal lattice. What do you mean by reciprocal lattice? The reciprocal lattice is having the vector. How do we characterize the reciprocal vector? If I am talking about reciprocal vector d star, then it has the magnitude. The reciprocal vector, we know in which direction our interplanar spacing is there. That means let's say I am talking about dhkl. Here we know the vector representing the magnitude as well as the direction of that interplanar spacing, right? He told us that, Ewald told us that to see to visualize these planes, to visualize these real planes in a three-dimensional real plane in a two-dimensional in a two-dimension, what we have to do, we have to go into reciprocal lattice. And how do we characterize the reciprocal lattice? We have characterized the reciprocal lattice in such a way that the reciprocal vector, the magnitude of reciprocal vector will be inversely proportional to, or will be the inversely that means the reciprocal of this real lattice or the real interplanar spacing. So that is how we have characterized the reciprocal lattice. Okay, so reciprocal lattice, how has Ewald characterized that the reciprocal lattice vector, because we know in this direction, let's say I am talking about origin x, y and z. If I am talking that this is my one plane and this is my d, then I have to take reciprocal. If I have to consider reciprocal lattice, then the dimension which I know the magnitude, then what will be the magnitude? D. So this is what he has characterized, and he has told that any vector in reciprocal lattice represents a set of Bragg planes. Okay, any vector in reciprocal lattice represents Bragg plane and can be resolved into component. If I am talking about dhkl in H, let's say a1 plus k, a2 plus l, a3. This is if I am representing any vector in a vectorial notation. Let's say a1, a2, a3 are my coordinates in real lattice. Then I can convert that real lattice to always the reciprocal lattice. Okay, this one he has proposed. And remember, mathematical one-on-one relation exists between real space and reciprocal space for orthogonal system. For non-orthogonal system, this relation, like we have told that a1 into b1 is equal to 1, a2 into b2 is equal to 2, a3 into b3 is, no sorry, not 1, yeah, 1. So all these relations that we are talking about, they all lie for the orthogonal system. Non-orthogonal system, these are little bit complicated. Okay, and here what we know that the reciprocal lattice vector will be always lying for orthogonal system. Reciprocal lattice vector will be always lying normal to the plane. So here this is a lattice plane, and the reciprocal, the vector notation or the vector direction of the vector reciprocal lattice vector will be normal. So when he proposed this thing, yeah, so these are all these features of a reciprocal lattice is normal to the real lattice plane. Reciprocal lattice vector, which I showed it here, is normal to the real lattice vector, and the magnitude will be the inverse of the interplanar spacing. Okay, now he after proposing all these things, he proposed another theory that is called Ewald's sphere of reflection, right? So what is Ewald's sphere? So Ewald's sphere is a sphere. Remember, this Ewald's whole concept of Ewald's sphere is imaginary. Okay, it is all it is not a real sphere, it is an imaginary sphere which he has visualized. So what, after defining reciprocal lattice vector, what he has proposed is that there is a sphere, okay, and the Ewald sphere is an imaginary sphere where at the center the crystal will be there, okay, and the radius of this sphere is always 1 by lambda. Lambda here being the wavelength of the incident beam. It can be any incident beam, okay, and most important thing, the crystal will be staying in the middle, and on one side of this thing, on one point of circumference, the origin of the reciprocal lattice will be there, right? And while defining reciprocal lattice here, how from here, from this point, let's say the origin was this much dense. What Ewald proposed, that if, when you have defined the reciprocal lattice vector, how do you define the planes? He told that all the three-dimensional planes in reciprocal lattice will be, let's say this is the origin, all the three-dimensional plane in the reciprocal lattice will be depicted as a point on the real lattice, will be depicted as a point on the reciprocal lattice. If I am talking this is an origin, then all these points which I am currently drawing, these all points, so points in reciprocal lattice are equivalent to planes in real lattice. I think our time has elapsed. I'll take a few more minutes and then we'll close. So Ewald proposed that points in reciprocal lattice are depicted, planes in real lattice, this is three-dimensional real lattice, are depicted as points in reciprocal lattice. If I am talking about this origin, then how will we put that which plane remains where? Then he told that the distance between any plane will be given by the reciprocal lattice vector, okay. So let's say this is 1 0 0, this is 2 0 0, this is 3 0 0, this is 0 1 0. This plane, that means this is 0 1 0, means this 0 1 0 point in a reciprocal lattice is giving us information about the 0 1 0 plane in the real lattice. So this is what, this was his proposition. So D star, if I am talking 0 1 0. So this is how he told us that you have to visualize which plane, or which plane in three dimension, or which plane in reciprocal lattice can be seen. So that actually solved all of our problem. Where the origin was dense, we are not able to see which plane got which plane was diffracting, which plane was not diffracting. When he told us to depict, or he told us to put all these three-dimensional real plane to a point in reciprocal lattice by the distance of the reciprocal vector, okay, in their particular direction, it solved all our problems. What did it do? We are able to finally visualize all the planes. So based on that, he proposed the sphere, the Ewald sphere concept. Where the Ewald sphere is an imaginary sphere whose radius is 1 by lambda, and where the origin of the reciprocal light hinges on one of its circumference. So that is the proposition that he has given, the Ewald sphere, okay. So here you can see reciprocal lattice viewed as tangent to this sphere, right? And here also same thing I have mentioned, and here why I have put only in positive direction, so you can see 1 0 0 2 0 0 3 0 0 0 1 0 0 2 0. Also there are reciprocal lattice in the negative direction, but yeah, here I have done. So Ewald sphere is always an imaginary sphere of radius 1 by lambda, where the origin of the reciprocal lattice hinges on one of its circumference. And what happens, let's say this is my origin of my reciprocal lattice. What happens when I rotate the crystal? Because I am considering my beam is coming in this direction. What happens when I rotate the crystal? When I rotate the crystal, in that case the origin of the reciprocal lattice remain as it is. However, all the other points which I am talking about, all the other points, they will rotate, okay. And how the diffraction is happening? The points which are coming on the Ewald sphere, these points are effectively a real plane in three dimension. This is a real lattice plane which I am seeing it in reciprocal lattice, this point. So when I am talking about this one, right, so this is an origin of the reciprocal lattice, Now currently none of these planes are on the sphere, on the surface of the sphere. So when I rotate this thing, the points here, the points in the reciprocal lattice or the three-dimensional plane in the real lattice, when I rotate this thing, the points which are coming on the surface of the Ewald sphere, only they will be giving us the condition of diffraction. Okay, so how they will be giving us the, so here two vector are important. One is the d star vector, so that is why, let's say this plane, if I am talking in terms of s naught, right, and here it is s vector, then corresponding to this I can draw the q vector. So same thing I have drawn it here. This is my s naught vector, my incident lambda, this is my s vector, my scattering vector. So far I am not talking about diffraction, I am talking about in terms of scattering. Okay, so this is my scattering vector, incident vector, this is my scattered vector, and here if you see, then this is my scattering vector. So when the scattering, so here I am getting two, and remember this is the origin of my reciprocal lattice, and this point, the distance between this point will be given by the d star of that corresponding to this thing. So when my d star of a particular HKL will be equal to the scattering vector, so this is the condition for diffraction. That means any point which comes onto the surface of the Ewald sphere, that means any plane in real space which comes into the surface of the Ewald sphere, that point will only give me this thing. And how I have characterized this thing? I have characterized sine theta. If I am talking about sine theta, so this is also d star by half. If you can geometrically calculate, sine theta will be given by d star d. Let's say I am talking this point as 230, d star 230. That means the in real space this is 230 plane. So you can see this is 1 by lambda and this is theta. So sine theta will be given by a naught OA, that means OA divided by OC, OA divided by OC. So putting all these value, I am getting lambda is equal to 2 sine theta by d star. Okay, I have got some sine theta is equal to lambda 2 sine theta divided by d star, but I know that I have already defined my reciprocal lattice vector as the inverse of the real vector. So if I put 2 sine theta divided by this d star, if I put 1 by d, then what I will get? Sine theta is equal to, here I am writing sine theta is equal to 2, sine theta, okay, lambda I will get, not sine theta, here I will get lambda, sorry, 2 sine theta, then I will get lambda is equal to 2d sine theta, and this is the condition of diffraction. Okay, which has been given by Bragg. But how will I physically visualize that? Whatever Bragg has written, whatever Bragg has given, whatever Ewald has proposed, whether they are correlating with each other or not. Here we can see the incident beam. As we rotate the incident beam, the points which are, whether I have drawn it, okay, I'll show it here. The diffracting planes, you can see the incident beams are coming, the scattered beams are coming, and when the same condition, this is in real space. Okay, and you can see while calculating, if you calculate the real space and how the real space and reciprocal space are correlated with each other. So these are the diffracting planes in real space, and this we have this diagram we have considered from the reciprocal space, considering that there is an Ewald sphere, there are different reciprocal points are there which are eventually three-dimensional planes in our real space. So if when you code this thing, then same thing you will get, q is equal to s naught, s minus s naught by lambda is equal to 2 sine theta by lambda. So this thing you will get same, okay, so this thing will get by n. So final condition you will get is n lambda is equal to 2d sine theta. So if you want to visualize how the diffraction which is occurring, how we are saying that the points which will be coming on the surface of the Ewald sphere, that will only be giving us the diffraction planes. So this is the real space versus reciprocal space correlation. And remember, I told that the radius of the Ewald sphere is 1 by lambda. That means the more of the wavelength of your beam, the less amount of points you will be able to intersect. Here you can see one chromium wavelength is high, right? So since chromium wavelength is high, this has been able to only detect 310 plane, 200 plane, 31 bar 0 plane and 1 bar 0 plane. When I am going from chromium to copper, my 1 by wavelength is decreasing. That means my radius of my Ewald sphere is increasing. Here I am able to access more number of planes, 220, 420, 5105, all these planes I am able to explain. From copper, when I am going to molybdenum, even the wavelength is less, then you can see my radius of my Ewald sphere is more, means I will be able to access more number of planes. That means my condition for diffraction, that is when the reciprocal lattice the reciprocal lattice point, when they stay on the surface of the Ewald sphere, that the condition of diffraction happens, that will be more, the probability of that thing of happening will be more here. Okay, so that is why also sometimes we will get more planes when we are using the molybdenum X-rays. Okay, and yeah, I think the time is not there, but quickly we can go through some of this question answer. Okay, we'll discuss. I'll tell. So choose the correct combination. Choose the combination of the statement which are true. X-rays are produced by knocking out the inner cell electron from the target material using highly accelerated electron produced with electron voltage. This is true. Okay, X-rays generated from a target has continuous wavelength and also has characteristic wavelength. X-rays generated from a target also has continuous wavelength. Yes, this is also true. Continuous and characteristics. Heterochromatic radiation with multiple wavelength are used for X-ray diffraction analysis crystal structure. This is wrong.
False.
Yes, okay. Continuous wavelength of X-rays is produced due to, okay, this is due to the reciprocation. This is correct.
Correct.
So 1, 2 and 4.
One, two.
Which one is correct? This one.
Third option.
Okay, yeah. So choose the correct statements about the characteristics wavelength of X-rays. On increasing voltage, wavelength of the characteristics X-ray will change. On increasing voltage, wavelength of the characteristics. No, this is not correct. K alpha characteristics wavelength is lower than K beta. K alpha is characteristics wavelength. No, this is also not correct. There is a critical excitation. K alpha characteristics wavelength. Just let me draw. K alpha is higher, right? There is a critical excitation to produce X-ray. This, I think, C will be the answer. Okay, on increasing, yes, C will be the answer. Because K alpha, wavelength of K alpha is greater than wavelength
Intensity
of
is
K
higher.
beta. Okay, so energy of K alpha is less than, but wavelength is higher. Okay, and yeah, this is a question regarding mass absorption coefficient. You are asked by a company to develop a material which will be used as shield for protecting workers from X-ray radiation. Remember, X-ray is carcinogenic. When X-rays are produced earlier, when X-rays are first produced in Europe, people used it as taking photographs. There are photographic studios of X-rays were there. So, but since they were carcinogenic at the time of at that time, people did not know about the negative side of the X-rays. So after a certain period of time, in and around Europe, there were a lot of cancer issues were there. So X-ray are always they are carcinogenic. So you should not put your hand or something directly below it. But the medical X-ray that we are putting sometimes to map our bones or something, when something has happened with us, those are actually very refined X-rays. But still they are also dangerous if you are getting exposed for a longer period of time. So among which you would choose? So by mass absorption.
Lead coated apron.
Sorry?
Lead coated apron.
Yes. So lead is one of the shielding material which is used, and due to this region, when X-rays are used, when you can see in many, all of the conventional X-ray diffraction, X-ray diffractometer, if you see, the entire setup will be covered in a glass. That glass is made of a plate glass. Because glass, this lead glass has high mu by rho, that is mass absorption coefficient, so it will absorb the X-rays, so it will not be harmful to you. Okay, so your cubic crystal lattice has the d spacing of 1.372 angstrom, 327 angstrom for the HKL plane of 222. What is the lattice parameter? Okay, HKL for a cubic crystal, I am just putting for a cubic crystal, the lattice parameter is given by 1 by d is equal to h by, what is the formula? 1 by d is equal to 1 by d square is equal to h square by a square plus k square by b square plus l square by c square. So since in cubic crystal all ABCs are same, so 1 by d square is equal to h square plus k square plus l square by a square. So you can write it here, a square is equal to so what is it asking, what is the lattice parameter? A square by h square plus k square plus l square is equal to d square, right? From here you can calculate the a square, the lattice parameter value. Okay. Calculate the short wavelength limit for, so yeah, short wavelength limit I have told that lambda SWL is equal to HC by, what is this, HC by EV, right? H is the Planck's constant, C is the velocity of the light, which is also a constant term, E is the 1.6 into 10 to the power minus 19 coulomb. Only thing, V is also given 25,000 volt. So I think this term coming something close to 12.4 into 10 to the power 3. I'm not sure, just check, put all this term divided by V. So just check what are the values you are getting, and all the units should be put in SI unit. So you will get the answer here.
That is 12400.
12400, 12400. Yeah, 12.4 into 10 to the power 3. Yeah, correct. So yeah. Which of the following statements are incorrect? So these are the questions also that can come, whether they are correct or incorrect we have to see. Statement 1 is the threshold wavelength limit below which no emission occur increases with applied voltage. The intensity of X-rays oh, where is the statement 2? I don't know. The intensity of the X-ray spectrum will increase with increasing voltage. Yes, this is correct. Okay, since statement 2 was is not there, so we'll leave this question. I don't know where it is, maybe some mistake happened. We'll go to statement question 7. In a simple X-ray scan, which of these affects peak position? So far we have not described, we have not studied about the peak position, but okay, X-ray wavelength, remember n lambda is equal to 2d sin theta. You can go through, you can use this equation. Peak positions means the d. Okay, no, yeah, peak position means theta, where the theta is coming. So the typical X-ray diffractogram, you will be getting I versus 2 theta. So and this theta will be giving you the peak position. Okay, and X-ray wavelength, yes, n lambda is equal to sin theta. As you vary the X-ray wavelength, accordingly the peak position will also change. Crystallite size and atomic number, in this equation crystallite size and atomic number will not matter. Peak, how they will not influence peak position, but these two will influence, we will study later. One of the major disadvantage that we will be facing while indexing our X-ray diffractogram, that is known as peak width. So we don't want our peak to be as wide as possible, we want them to be as minimum wide as possible. And unit cell parameter means D. Once we get D, based on the crystallographic orientation, will be if we know the plane HKL, then we will be getting unit cell parameter. These are referring to A, B and C. So which of these things, statement 1 and statement 3, which one is this? C. Okay. What is the primary information obtained from an X-ray diffraction pattern? The arrangement of atoms in a crystal lattice, the size of the crystal, the composition of the crystal, the crystal's color and transparency. Arrangement of atoms, this is also another concept that we will get, like how the crystals are arranged based on their position, because as we n lambda is equal to 2d sin theta, as we vary the theta, the position will also change, the d will also change. So we will be able to know how the atoms are arranged. So basically we will be studying another term known as structure factor. So this structure factor will also give us more information. Which of the following statements are correct? So the diffraction pattern coming from X-ray diffraction experiment is the intersection of all the cosine clones in 3 dimensions. This is correct. This is what I was talking about in Laue's first law, second law and third law. That means when all the 3 laws are satisfied, then only the condition of diffraction happens. The magnitude of a reciprocal lattice vector is inversely proportional to the distance between adjacent crystal plane. This is also correct. And Bragg's law is only satisfied by the points lying on Ewald sphere. Yes, this is also correct. So 1, 2 and 3, all of them are correct. Which of these are not involved in the diffraction of X-rays through a crystal? I think you will be studying this in the next class also, but I have told this in the this class regarding scattering. So scattering means all this scattering are happening due to electrons, and because there is a term in elastic scattering where mass is involved, and once the mass is involved, the nucleus has sufficient mass, so it is not able to do the scattering. So electron scattering, nuclear interaction, crystallographic planes, constructive interference.
Nuclear interaction.
Nuclear interaction will be there. How the nuclear, why the nucleus actually does not interact with the
Because one position.
and what is the smallest d spacing that can be measured for a given wavelength? So here if I am talking about n lambda is equal to 2d sine theta. Let's say I am talking about sine theta, and this maximum value of sine theta, if I am talking about, this is 1. If I am talking n lambda by 2d, this is sine theta. Okay, now I am considering that my first order reflection is happening. That means lambda by
Yes, sir.
2d.
Yeah.
Sine theta, and this sine theta maximum can be 1, so lambda by 2d should be less than 1, so the option will be A. And a crystal has a cubic unit cell parameter, that means A has been given, wavelength lambda has been given, at what angle 2 theta you would expect 100 peak. So HKL value has been given. From HKL you can calculate D, right? And yeah, from HKL and A both you can calculate D value, A and HKL. Then you need to put n lambda is equal to 2d sine theta. So D value you can calculate from this two, and then lambda is given. N you can take is at the first order reflection, and then you can calculate this thing. Okay, yes. So that will be the end of our session.